All right, we got some formulas to use when we're dealing with light. We can write some of those out. We got we could also write this velocity. We got wavelength is equal to speed of light over velocity. Okay, so what is this question asking? It's a cool question. We got oxygen double bond. So this is oxygen gas. This is what we breathe. It's what we need to sustain life. And so essentially, what type of light could break this? What photon could break this? And so we're going to be looking at something higher than visible light, probably higher than UV light, which is good because if those things broke down oxygen, then we would have a hard time living. And so it's going to be something more in the X-ray type range, likely, or gamma. So let's figure it out exactly to the nanometer. And that's what our problem is asking for, is nanometers. So we're given an amount of energy. Now it's kilojoules per mole, and we're going down to a single photon. So we're looking at an oxygen molecule. So we got some work to do here. What light? And so we're given energy, so that's here, and we're looking to solve for wavelength. Okay, but we're also given kilojoules per mole, and we need just joules because our constants won't be canceled out unless we have joules. So first thing we had to do is get to joules from kilojoules per mole. So let's write 498 kilojoules per 1 mole of photons. Or of bonds, sorry. So I'm going to say 1 mole has 6.02 times 10 to the 23rd bonds that we're breaking. And then there are 1,000 joules per kilojoule. So let's start with that. I'm going to use my EE button. I'll show it on my calculator here. So we got 498 divided by 6.02. Here's my E button. And then I'm going to times that by 1,000. So I got 8.2724 times 10 to the minus 19th. So 8.2724 times 10 to the minus 19th joules. That's to break one double bond. Okay, so what wavelength is that? So there's our energy. So now we got to rearrange. So I'm going to multiply both sides by wavelength and divide both sides by energy. And I get wavelength equals HC over energy. So I'm going to plug in my wavelength. And again, that wavelength is going to be in meters and as for nanometers. So let's use some of our constants here. 6.626 times 10 to the negative 34th joule seconds. Speed of light, 3.00 times 10 to the 8th meters per seconds minus 1. And then my energy was 8.2724 times 10 to the minus 19th joules. So let's look at cancels, or units. Joules cancel, seconds cancel. We got left with meters. So let's plug that in. 6.626 EE to the negative 34 times 3.00 EE to the 8th divided by 8.2724 EE to the negative 19th. And I get 2.4029 times 10 to the minus 7th meters, which is a good sign. That means I'm in the meter range. So 1 meter is 1 times 10 to the 9th nanometers. So let's multiply that by 1 EE9, and I get 240.29 nanometers. Let's look at our, we got 3 sig figs. So it's 240, so I'm gonna write 2.40 times 10 to the second. So 240 nanometers is definitely, visible light ends at 400. So that actually might be in the high energy UV range. 2.40. There we go. So 240 nanometers to get the wavelength of light that would break a double bond. So 1 photon, 1 double bonded molecule. But the key is using the formulas, how we need to understand what we're given. Again, defining that problem, we're given energy, but we got to solve for joules, and then we can cancel some units from our constants.